Today, I am excited to present our research titled Investigation of Different Dark Fermentation Strategies for Enhanced Biohydrogen Production from Lignocellulosic Wastes. This work was conducted at 9 Eylül University under the supervision of Professor İlgi Karapınar. This study focuses on enhancing biohydrogen production from lignocellulosic waste via dark fermentation, using a single waste stream in two complementary ways: a sugar-rich hydrolysis as substrate and biochar as a process-enhancing material. Why peach pomace? Turkey is among the top 3 global peach producers with over 1 million metric tons annually, and roughly 10% is discarded as pomace during processing. Our goal was to transform this waste management challenge into clean energy. This characterization shows a very clean heavy metal profile, eliminating the need for detoxification. The C/N ratio of 35.3 is ideal for our Clostridium species. Critically, inherent trace elements like iron and nickel will act as cofactors for hydrogenase activity. Combined with its high carbon content, peach pomace is a perfect candidate for both fermentation and biochar production. Peach pomace is rich in...
Sunumu kesiyorum ama kamerayı açabilir misiniz acaba? Şimdi sunumu yapanı görmek gerekiyor online olduğu için.
Kusura bakmayın, ben unutmuşum.
Vay ya,
Kusura bakmayın.
teşekkür ederim.
Sağ olun. Peach pomace is rich in fermentable sugars, but at high loadings, FBA accumulation drops the pH and triggers a lactate shift, diverting metabolism away from hydrogen production. This is exactly the challenge of our study addresses. So, to address the challenges of pH drops and metabolic shifts, our strategy was to integrate biochar into the fermentation system. Biochar serves a dual purpose here. First, it acts as a natural buffer, helping to maintain pH stability. At the same time, its highly porous structure absorbs inhibitory compounds from the medium, protecting the bacteria from metabolic stress. The most original aspect of our work is single-dose dual valorization concept. From a single dried and ground peach pomace stream, we created two parallel outputs. Acid hydrolysis of fine particles yielded our sugar-rich substrate, while pyrolysis of standard particles produced our biochar support. Both were then combined in the dark fermentation reactor. One waste stream, one closed-loop system. Our research methodology followed a systematic 6-step workflow, from the initial preparation of the waste to acid hydrolysis, pyrolysis, and detailed biochar characterization. This led to our dark fermentation trials and a final performance evaluation. Now let's look at how we optimize these stages. We optimized biochar production using a box Benken design with 17 runs, varying 3 parameters: pyrolysis time, residence time, and heating ramp. Our goal was to engineer ideal morphology for bacterial attachments, chemically maximizing aromaticity while minimizing oxygenated groups, and physically minimizing island size to maximize surface area and microbial colonization. And this slide shows our laboratory setup for producing this optimized biochar. A notable detail in our methodology was to use the graphite powder as an oxygen scavenger. We utilized graphite powder as an oxygen scavenger to maintain an oxygen-limited environment inside the muffle furnace. So, for the CC band, the model is highly significant, with temperature as the dominant factor, F value of 59.41. Residence time and ramp showed no significant effect, and the insignificant lack of fit confirms a good model fit. For the CO band, the model is again highly significant, with temperature as the dominant factor, Critically, a significant temperature ramp interaction means these two cannot be optimized independently. The CH band is our most complex response. Both temperature and ramp are independently significant, with two significant quadratic terms confirming non-linear behavior. R square of 0.96 is the strongest among our FTIR models. And lastly, island size is our strongest model. All quadratic terms are significant, and ramp interactions with both temperature and time are critical, confirming that heating ramp is the key parameter controlling surface methodology. These quadratic response surface equations represent the mathematical core of our engineering approach. They allow us to see exactly how temperature, time, and heating ramp interact. These surface plots confirm our statistical findings. Plot A shows carbonization rising sharply with temperature, while plots B and C show nearly flat surfaces, confirming that neither ramp or time adds significant effect once temperature is fixed. The CH plots show the most complex behavior. Plot A reveals a curved twisting surface, confirming nonlinear quadratic effects. Plot B shows strong curvature along time ramp axis. This slide summarizes our model validation. In summary, by simultaneously maximizing aromaticity and minimizing island size, all models showed strong statistical significance and predictive capability. The validated optimum conditions are 650 degrees Celsius, 8 minutes, and 20 degrees per minute heating ramp. We verified the quality of the optimized biochar using a 4-step characterization toolkit. FTII for surface chemistry, XRD for crystalline structure, SEM for morphology, and EDS for elemental composition. The characterization confirmed our targets. XRD showed a turbostatic carbon structure ideal for biological use. Oxygen to carbon ratio dropped to 0.16, confirming high carbonization, and SEM revealed porous island-like structures averaging 30 nanometers. Additionally, EDS detected potassium on the surface, meaning our biochar acts not just as a physical support, but also as a macronutrient source. For the acid hydrolysis optimization, we again applied a box-Benken design with 17 runs. Our goal was to maximize sugar recovery while minimizing inhibitor formation. We investigated 3 independent variables: pH, temperature, and hydrolysis time. Each tested at 3 levels as shown in this table. Here you can see the laboratory scale autoclave and centrifugation steps we used to obtain the final sugar-rich hydrolysis. These ANOVA results confirm our model is highly significant with R square of 0.99. The dominant factor is quadratic pH term, confirming a clear optimum rather than a linear trend. And these surface plots confirms our ANOVA table. Plots A and B show a clear hill-shaped surface. Sugar recovery peaks at pH 5-6 and drops sharply at both extremes, confirming the quadratic pH effect. Plot C shows that higher temperature with longer time consistently improves recovery. The optimum is 5.8. The optimum is pH 5.8, 100 degrees, and 60 minutes. The model predicted a total sugar concentration of 41.28 grams per liter at the optimum conditions. In our laboratory validation experiments, we achieved exactly 43 grams per liter of total sugar. This proves that the high reliability of our predictive model, achieving an 86% sugar recovery. The 43 grams per liter hydrolysis showed no toxic heavy metals. However, iron, nitrogen levels were below the threshold optimal hydrogenase activity. With both our biochar and sugar are ready, we proceed to final stage. We conducted Bach-der fermentation test using Clostridium pasterianum. As you can see in these photos, the experiments were carried out in an anaerobic serum bottles inside a rotary shaker to ensure uniform conditions across all trails. In our control runs without biochar, low sugar loading produced hydrogen efficiently, but at the highest loading, despite high sugar consumption, yield dropped to just 0.26 moles of hydrogen per mole of total sugar. At high sugar loading, lactic acid accumulated massively and was never depleted, while acetic acid was suppressed. At 5 grams per liter biochar, the system clearly recovers. Hydrogen production is now sustained even at high sugar loading, with consistent yields across all concentrations. These acid profiles confirm the mechanism. Lactic acid is produced but then depleted, evidence of the biochar absorption. 12.5 grams per liter of biochar inhibition at high sugar loading was successfully mitigated. Cumulative hydrogen reached 244 millimeters. This graph delivers our central conclusion. Each sugar concentration peaks at a different biochar dosage. Optimal biochar dosage is not fixed. It must be tailored to the metabolic load of the system. Our performance is highly competitive with literature. Importantly, while many studies use synthetic glucose, we worked with real agro-industrial waste, a far more challenging substrate. In conclusion, we validated the single-source dual valorization strategy from peach pomace, proved that biochar must be engineered with specific heating rates for optimal morphology. Confirmed biochar acts as a metabolic buffer by maintaining pH above 5.2 and absorbing lactic acid. And I have two key recommendations. First, transitioning to continuous systems such as CSTR or immobilized bed reactors to evaluate long-term biochar stability. Second, pilot-scale experiments to address incomplete sugar consumption at high loadings and mass transfer limitations at larger volumes. Finally, I would like to express my deepest gratitude to my supervisor, Professor İlgi Karapınar, and thank you all for listening.
Thank you very much for your presentation. So, if there is any question, we would kindly ask you to ask it now, please. Is there none?
Thank you.
Okay, so there is no question, I guess. I would actually ask a very short one, if you allow. Are you gone?
No, I'm here.
Yeah. So, what was the challenge of the study that you faced when you were doing your test and so? What was the most challenging part of the work, just for the record?
Yeah, I think the most challenging thing was the characterization of biochar to select which biochar should we use to maintain the fermentation process. Because we tried a lot of different concentrations of peach pomace and a lot of different heating ramps, temperatures, and times to produce biochar. We tried to prove that biochar is not just a charcoal, that we can use it to maintain our fermentation, and we thought that biochar would help us to pH stability and physically, and we tried to prove that. I think the most challenging thing was to select which biochar we should choose, because we produced over maybe, I don't know, like 50 different biochars, and we tried to select which one is the best one.
Thank you very much for the explanations. So now we can
Thank
pass to the next presenter, if there is no question, of course, and we are running out of time. So we would like to invite Mr. or Miss Taufiqurrahman to start with her or his presentation. Thank you.
Okay. Thank you so much for suggestion. Assalamualaikum. Merhaba hocam. Merhaba arkadaşlar.
Merhaba, aleykümselam.
Benim adım Taufiqurrahman. Şimdi ben Bursa Uludağ Üniversitesi'nde doktora çalışıyorum. Doktora öğrenciyim. Aynı zamanda ben Indonesia'da bir üniversitede çalışıyorum. Bugün konferansta sunum için İngilizce
Hiç problem yok. İngilizce, Türkçe hepsi geçerli. Nasıl sizin
hocam.
için uygunsa.
İngilizce konuşacağım hocam. Okay. To present my research here in this conference entitled Integrating Religion.
I don't know if it's just my problem, but we can't get your voice well.
Yeah, it is the same.
No, it was good. It was good in the beginning, but now not. Yeah. Oh, no, still not. No, I think there is a problem with your mic, or I don't know, the internet or what. No, we can't understand what you're saying. I don't know. Do you have another device, or if you're using earphones, it's possible to change them, to change the type of maybe a mic. We really can't hear your voice or understand.
Can you hear my voice?
Yes, better now. Yes, yeah, it's good now.
Okay. Maybe because I use mobile phone. Earlier I used my laptop, but my laptop suddenly crashed and turned off.
Oh, yeah, that's sad, because even the screen you're sharing is so small, but we can manage somehow. So if it was a computer, it would be better. Anyway, you just keep speaking and presenting.
My voice right now is
Yeah,
clear?
yeah, it's good. It's good now. Yeah, it's clear now.
Okay. So I need to turn off my video. Maybe it's make clear for my voice.
No problem. You can switch it on in the end, because we're gonna need to to see actually the presenter.
Okay, thank you so much. So my research today is about integrating religious activity intensity as an anthropogenic modeling Masjid environment of Indonesia and Turkey. This about urban runoff modeling has traditionally focused on rainfall and surface characteristics as the primary drivers of
I'm sorry. I'm very sorry to interrupt again. Your voice is coming and it's kind of moving. Are you moving the phone or the device? Sometimes it's good, sometimes it's going. So
No.
that's quite strange. So if
Yeah.
it's possible to keep it stable, it would be maybe better.
Okay, I will try to continue.
Yeah. Yeah, this is a problem because we can't hear anything. So nothing is coming through.
Can you hear my voice?
Yes, now we can.
Okay, let me continue.
Yeah.
Most conventional runoff models still assume that runoff is governed mainly by natural process. Meanwhile, structural human water use is rarely incorporated explicitly into the hydrological framework itself. And right now, socio-hydrology research increasingly demonstrates that hydrological systems are closely interconnected with human behavior. Most previous study, however, have focused on large-scale systems such as irrigation or watershed analysis and so on. So in contrast, relatively little little attention has been given to smaller scale but repetitive activities that generate concentrated water input on daily basis. This is why I selected Masjid environment as the focus of this study. So Masjid is represent a highly structured environment where water use occurs repeatedly through ablution, sanitation, and routine facilities activities. These activities occur predictably throughout the day, and it involves concentrated user groups. So Masjid activities provide a uniquely structured behavior system because ablution patterns occur repeatedly day by day at relatively fixed time with relatively consistent water use behavior. This makes masjid environment particularly suitable for analyzing interaction between a behavioral process and runoff generation. So based on this background, I, I developed a new behavior-informed hydrological framework called Religious Activity Intensity, or RAI. This RAI is the main proposed framework of the study. It was specifically developed to integrate a structured human water use behavior into the conventional runoff modeling. So the study has three main objectives. First is to develop the RAI framework itself. Second, to evaluate how behavioral water use contribute to runoff under different rainfall conditions. And third, to examine how spatial context influence framework So the framework extend the conventional curve number method by incorporating behavioral influence directly into runoff estimation.
It's we have the same problem back. It was good lately. If could we move a little bit fast because we still have like 3 minutes to go, more or less.
This simulation propose AI framework. I developed a simulation based on representation using 4 Masjid environment with comparable spatial characteristic of approximately 2,500 square meters. And this environment were also were not treated as direct implementation site. They were used as a representative scenario design to reflect conditions that reasonably comparable. Also, and if we talk about spatial context, concentration tend to be higher. So the first major the most significant behavioral influence appear under the 10 millimeter rainfall scenario. The behavioral contribution accounted for approximately in semi-urban environment. This suggests low rainfall intensity increased, rainfall gradually became the dominant cycle.
Okay, Mr. Taufiqurrahman, if possible, can we conclude, please, because time is up?
Okay, I will. So this study maybe emerge. Another question that may emerge is whether this religious activity like outside the masjid environment. I said Yes, it conceptually, yes, the framework can be extended to other activity-intensive environments such as campus, transportation hubs, school, or commercial facilities, and other public space, whether structure, water use contribute to runoff generation. But as I said earlier, this framework will be more effective in repeated activity than water use behavior. They still have several limitations. Study and future will focus on. Finally, to conclude, this study demonstrates that religious activity intensity consistently increase runoff across different rainfall conditions. It's overall the proposed RR framework demonstrates that structured human activities can be integrated into hydrological modeling in a physically consistent and analytically practical manner. So I hope this study can contribute to development of more behavior-informed approach. So thank you so much for your attention.
We thank you, Mr. Taufiqurrahman. I'm particularly sorry because the study was interesting, but we couldn't hear almost 70% of it. Of course, we can read the lines, and it's also very small. But anyway, I think that it's quite interesting study. I wish it could be better. So since of our time constraint, I would maybe if there is a single question, we can have a question. Otherwise, we have to move to the next one. It would be the better choice here, or even just move to the next one and keep the questions inside. So if you have any question to Mr. Taufiqurrahman, you can ask him privately. That would be better to keep the time flow optimized. Thank you very much. All right. Now the presentation is actually mine. Let me share my screen. So I'm Alif Diambu, PhD Mechanical Engineering. This work was done in together with Professor Mehmet Çevik. So it's about the end life management of biocomposites. We actually try to assess the biodegradability and recycling of these type of materials. From the picture you see in the right side, so it's about compounding natural fibers with plastics or biodegradable sources from plastics. And then after compounding, we have products coming from this compounding. And from this
Hello, sorry. Can you turn on your camera, please?
yeah, sure. Oh, I forgot that too. I'm the presenter, but I forgot the camera. This is strange. One second.
Yeah, it's okay. Been there.
Yeah, just a second. All right. So I was saying, as you can see from the picture or the figure in the right side, it's a cycle. So we have the material after production, it goes to the damp, let's say damp, or we have to, it's the end of life of the product. So we generally, let's say, think that's they are, when we talk about biodegradable material, they are totally clean. So there is no impact into the environment. But the real problem is people should be informed about the disposal process of these materials after using them, how they should be disposed so that they don't harm the environment. So that was the purpose of the study. And then I already talked about the meaning of biocomposite, which is the compounding of biosources like fibers with plastic to get materials that will perform better environmentally speaking. So when you throw them in the environment, you're gonna get less bad prints into the environment. Let's call it that way. So what we want to have is if we can lower the environmental impact of this material. Basically, we expect it to be that way. It's the way actually people understand it. When we talk about biocomposites and biodegradable materials, we expect it to behave that way. But it can't be that way if you don't follow very specific steps so that we have the end of life well managed. And then for that, we conducted this study for awareness and also to actually inform people what should be the way of interpreting or maybe behaving when we have to deal with the biocomposite materials. So the actual question that misses is what happens in the end of life of product from bio sources. And the part of what people actually focused a lot is the high, actually, let's say the upstream focus, which is renewable feedstock and the process optimization. So most of studies, they just work on optimizing the process and get the better outcome of the compounding. Let's say mechanically speaking, they expect to get better mechanical behavior or maybe thermal behavior, but they don't see what actually happens after the life of the product. After it's the end, okay, we have to throw the product out. And that's actually the aim of the study. So they generally neglect the end of life, the landfill and the disposal part of the work. And then the other part concerning the composting or recycling is also under evaluated or considered. So we have to find a way to close that gap. So why is it critical, this gap? So neglecting that actually is a failure, and it's going to cause maybe much more damage than using normal product we have, because we think that something is going to happen one way, but it actually happens the other way. So we have to shift our way of thinking. Of course, it's not wrong. I can't say that these products are not biodegradable. Of course they are, but we have to consider the best way possible of dealing with them. So material innovation without disposal planning is equal to deferred pollution. So the paradox is we actually promote the material and environmentally preferable, but those material can generate additional environmental burdens if there is not a proper management in the end of their lives. And then we have some of those paradoxes as well, which is the label we give biodegradable, but to get a material to degrade to be biodegradable, we need some conditions. For instance, it requires specific temperature, let's say 50, 60, and which we can't find everywhere. So it has to be controlled. But if it's not the case, we can get adverse situations such as we have 25 more portent than CO or carbon dioxide in the environment. And then we have that claim of biorecyclability. So fiber and pneumatic separation is actually technically, it's difficult. We can't separate them. So for that reason, it leads to downcycling or maybe incinerating those products or those bio composites. The incineration is actually what we use to prevent from moving from our traditional plastics to biodegradable or biocomposites. Since there is not a good management, they also end up being burned and harming the environment as well. So it's not a closed loop. So it's a loop we actually wanted to get closed, that we can recycle again. We can go with the processing those materials once or more, actually more than once. But most of the time, it doesn't happen that way because people need awareness, and we actually need a good management system for that. And there is also a confusion into people behavior. So we say green. So it's a good label, okay, saying green. But with an improper disposal, this is actually gonna contaminate the environment, the very environment we are working to saving. So these biocomposites are neither inherently sustainable nor inherently unsustainable. So the environment performance depends on the availability of the end of life management system. So for some terminology, maybe we can use them. We have the bio-based terminology, which is everything that is from renewable biological origin. Biodegradability, compostable bioplastics, or type of plastic who actually are based from bio materials, or let's say plants or so. And then we have the biocomposites I talked about. Okay, so there has been studies actually working on the same topic. We have problems like infrastructure gap. We have to close first, so we have a system to put in place so that we can follow the end of life of those products. We don't have adverse situations after that. And we can give here an example such as PLA, polylactic acid. Some researchers have demonstrated that after 12 months in home compost, this material or this plastic largely stays intact. So the biodegradation somehow stops. Okay, so this is another way of this is another problem, let's say, that actually requires people to look into and to find better solution. And then we have those gas, so methane gas, that can be dangerous than the carbon dioxide that can arise from those material flowing in the environment. And then we have the recycling contamination that goes together with them. So we have a part of the work that is theory and the reality in the field, okay, the reality we actually live with. And we have to find a way to keep it harmonious, okay? What we know as theory and the reality in the field, make sure that gap is closed as much as possible. So the incineration and the landfill is the actual last destination, unfortunately, if we don't get it well managed. And here we got some case study. The first case study is the Peliac caps, for instance. They are certified compostable, but still, for the case of the US, there is only 5% of the municipalities in the US that has actually a system to compost them, to collect them and compost them. And most of them, they end in landfill and then therefore generating methane. The other case is in the automotive panels. So they use hemp or flax together with the polypropylene in the panels. Of course, we say that, of course, it is weight savings. But when we go into the end of life, so we have to separate or to biodegrade the biocompost or the panels. They are generally shredded and incinerated or maybe landfill instead of reusing them. Okay, let's say you process them again, and you have to, after compounding and so, it doesn't happen because the system now doesn't allow that. So we need a system to better manage those products. We have also the case of marine packaging, same situation. So to finish with this study, we actually need a path forward, okay? What to do from myth to reality. The first one is we have to design our system to be realistic and to ensure that the end of life is well managed. So staying with the known standards to avoid hybrid composite that can actually harm the environment instead of really solving the problem of not degrading or non-degradable materials we know, like neat polypropylene, neat different type of plastics. And then we have to ensure that we have a standardized system that we sort out the materials. So we already have this system where we can standardize our trashes, where we have plastic here and we have glasses here or paper based on biological waste. We can also do the same with standardizing our bio materials or biocomposite materials when they are in the end of their lives. Like a green for industrial compost only. So we have a yellow to be checked locally and the green general waste only. Some type of course, there are already countries that actually are implementing this, but a very specific focus into biocomposite materials, that's something, it's something that needs to be still done or maybe evolved. So we also need investment. So we need to invest into infrastructures. Without infrastructure, the end of life is unsure. So we're gonna go back to the very beginning, that point where we were trying to solve the environmental issue of waste. So also the last and the very important part of this study was about awareness. So we have to educate people, to make them understand that what they say or they hear is not always the reality in the field. So they need to be educated and to work so that the end of life of products are actually or give us what we actually expect from them. Okay, not harming the environment by the contrary of it. This is basically the aim of this. This was basically the aim of this study. Now, if you have any question, I'm ready to get it. Thank you very much. I'm sorry, I got disconnected somehow. Can we move to the next, or if you have a question, we're ready to get it. If not, can we move to the next presenter? Mr. Garba Ismaila, are you here?
Hello, everyone.
Yeah, hello. So you can put your presentation, please.
Okay. So I can start now?
Yes, of course, you can.
Okay.
So we can make it faster because we still have time constraint here, please.
Yeah. Let's see. So you see?
Yes, we can see it, no problem.
Okay, okay.
proceed.
So, so, hello everyone. I'm honored to present to you today our research about between local awareness and geochemical reality. So, an
Could you
integrated.
could you get the screen bigger? Could you press F5 to full screen, please?
Okay. You see now?
Yeah. Can you take it to full screen if possible?
Okay. Come.
You press F5 from your keyboard. That's gonna do it. F5.
F5.
Monsieur Ismail, vous parlez français, n'est-ce pas? La touche F5 peut le faire.
Oui, F5, je suis sur F5, juste pour partager, non?
Non, non, ça c'est pour agrandir l'écran, pour qu'on voit l'écran en entier.
Ok, j'arrive.
Ou sinon, on peut continuer, hein, parce qu'on n'a plus de temps. Il nous reste pratiquement 9 minutes. Donc, si possible, vous pouvez aller directement les grandes lignes et aller à la conclusion. Thank you.
Oh, Dieu. Ok, parce que là,
D'accord, vous pouvez
F5.
continuer alors. Il n'y a pas de problème, vous pouvez continuer.
Et maintenant, ça va? Maintenant, ça va?
Non, c'est la même chose, mais vous pouvez continuer, quoi. We can continue, no problem.
Ok. I'm sorry. Ok.
On peut directement passer, we can move to the method and we move
Now
to the
you see?
conclusion. It's the same, we see, it's fine.
Okay. So, about our study context, artisanal and the small scale gold mining is one of the main livelihood our country. So
Yeah,
in Niger, it's
now we only see the first page. The first page only we're seeing now. We are only seeing the first page, the cover.
Okay.
Can you move to the page you are explaining now, please?
Yeah, I'm coming. Ça va maintenant?
Non. Vous pouvez utiliser la touche de direction d'en bas pour mouvoir d'une page à une autre.
Ok, c'est ça que je fais, mais attendez. C'est bon maintenant?
L'écran n'est pas encore venu. Oui, c'est bon maintenant. C'est bon maintenant. Vous pouvez continuer. Faisons-le
Ok.
vite parce qu'on n'a plus de temps.
Ok. So, idea about our study context, artisanal and the small scale gold mining, ASGM, is one of the main livelihood activities in West Africa. So support millions of people through rapid and largely informal expansion over the past 2 decades. About Niger, is one of the main livelihood activities in Niger. So, so our study focus on Issa. Issa, it is a region of Niger. So where our previous research documented rapid expansion. So 1 to 40 square kilometer in just 3 years. So About problem statement, the rapid expansion I just described raises major environment concern. We observe with the sprint soil degradation, pressure on water resources, and threat to local agro-pastoral sustainability. So look, our objective following this problem statement, my research aims to fulfill one main objective: to assessment the environment impact of ISGM at the Issa site using an integrated assessment. So to achieve this, I have defined three specific objectives. The first, to analyze the factor influencing how miners perceive impacts on the environment. Second, to evaluation. So to evaluation the actual contamination potential by looking at the geochemical composition of mining residues. So, and finally, to compare these two dimensions to provide better informed environmental management strategy. So this is a study area. This is a social survey about methodology. Donc, we do face-to-face interview. You have again three sections: socio-demographic, environment perception, and mining practice. So you have this statistical analysis. Donc you binary logistic regression about model. Donc, after survey social, you have again geochemical assessment strategy at the Issa. So for the geochemical assessment, we collected 44 samples across the site, including tiling, soil house, and house rock. The water from both mine wells and community boreholes. Yeah. So this is the first result about social survey. This slide presents the social demographic profile on the surveyed miners. Most respondent women representing 18% of the sample. So you have gold mining as mine occupation, main reasons for choosing them again. So about gain result, main determinants of miners' environmental perception. So this table presents the main determination of miners' environmental perception using binary logistic regression. So we modeled three tips on perceived impacts: soil, water, and agro-pastoral. So cane feeding nationality is a strong predictor. Nigerian males are less likely to perceive soil and water impact compared to migrants again. Role on seed matters significantly. Finally, seed chefs and leaders show high perception across all three domains again. So about our results in geochemical analysis for trace metal accumulation in solid matrix. For solid matrix, you have soil, tiling, and rock. The small mine in Issa.
Sorry to interrupt. With time's up. If possible, can we just find a way to end it up?
Okay. We have again metal mobility in the leaching condition. So, I pass. Groundwater quality assessment again, about mining area, communal resources again. So, about discussion, social perception. Voilà. So, our feeding on social perception reveal differentiated awareness. Perceptions vary by nationality, city role, and length of stay. Decision makers and those with longer to know show significantly higher odds on perceiving impacts. So, our study quantified these differences for the first time at the Issa region, for in Niger. So, about the gap between perception and geochemical reality. For mining requires some impact bite and estimate the severity and chemical contamination, what we call invisible risks. High toxic from arsenic, chrome, mercury, and matters we humans don't perceive immediate danger. Yeah. So about mining residues, the pre-contamination reservoir. So about this, first, tiling concentrate the highest levels of trace metal, arsenic, chromium, mercury, and lead. Second, mobility or leaching tests prove these metals are not stable and can be easily released into the environment. So about hydrological connectivity and public health risk. So we find that contamination is not restricted to the mining parts because the values in community sorry. Yeah.
So
Sorry.
is there a very final
So,
discussion or conclusion from the
so
study, please? Mhm.
yeah, for conclusions and recommendation about my study. So, in conclusion, our study confirmed that the ISA faces a double challenge. On one hand, we have a clean geochemical contamination of soil and water. On the other hand, the people working they do not fully perceive then the invisible chemical risks. The gap is a blind spot that makes the situation dangerous for both miners and the surrounding population. For our recommendation about this, we recommend a twofold strategy. Technically, we must isolate the tiling hotspots to stop the flow of toxin. Second, socially, we need to bring the awareness gap through targeted education. It is not enough to just inform. We must engage the miners, especially those with low perception, to transform these results to safer local practice. That is a future research perspective because we don't have mineralogical characterization to confirm trace metal species and reference resource apportionment ongoing.
Okay.
So
Thank
this
you very
is
much.
reference.
Okay. Thank you very
Thank
much.
you. Thank you very much.
Thank you very much,
Sorry.
dear Dr. Garba. So now I think we out of time. It's better if you have questions to go privately to the authors. We have to move to the next presenter. Is Mr. Firi here? Mr. Clifford.
It's Piri. Thank you.
Mr. Piri. Okay, please, you can start your presentation.
Okay. So I'll share the screen.
Yes, please.
Okay. So good afternoon, esteemed chair, organizers, and my fellow academic peers. Today I'm pleased to present my research on the genetic algorithm optimization of buckling restrained brace placement in reinforced concrete frames. Before I begin, I'll summarize the journey by first explaining the problem, the structural problem that I'm trying to consider, and the solution as well that I am proposing, which is the buckling restraint braces. These will offer an optimal solution to the structural problem that is introduced. And as we delve into this, I will first provide some context into the matter. I'll first like to draw your attention to the left side of the screen, where there's some pretty horrifying statistics, though horrifying, they must be explained. In the year 2023, which is roughly 3 years before now, there was a very tragic earthquake in which the deaths of over 50,000 was recorded, with an earthquake magnitude of 2 actually, of 7.8 and 7.7. As a result of this, 11 million, almost 11 million people were displaced from their homes. And from a structural point of view, it was noted that the structures had experienced soft story mechanisms, weak flow collapses, and my apologies. Okay. They experienced weak soft story mechanisms, weak flow collapses under lateral loads, much like how putting a large elephant over a small wooden stool, the outcome of that would be obviously it collapsing under its own weight, which is something that we strive not to attain in structures. Another thing would be non-ductile column failures. This was also noted amongst the structures due to insufficient confinement restraint reinforcement, poor beam column joint detailing. This was especially noted in pre-1990s reinforced concrete constructions. Even to add to this, the most common form of mitigation for this or retrofits are shear walls, and the result, much as they are helpful, they add massive stiffness and cost and use up a lot of floor space. In this case, propose
Mr. Clifford, your presentation is not moving. We're still in the context page.
I hear.
Okay.
I'll definitely pick up.
Okay, thank you. So if we can try to move it a little bit, time.
All right. I understand. So my proposal is the buckling restraint braces, and these are a high-performance seismic device that acts as a structural fuse. Unlike the conventional steel braces, these experience the conventional steel braces experience buckling under compression, but the ones that I propose have a concrete casing around them, and this can be shown in the next slide. As you can see, they consist of a steel core, which is on the right, and a concrete casing that surrounds them. These their special characteristic is the energy dissipation, which protects the concrete frame by yielding predictably. So I move on to the next slide, and here I cover the dilemma that I experienced. So as we equip the RC frame, we carry out a special test, an analysis called pushover, and as a result, we obtain the graph that we see up in front of us, the capacity curve. And here it can be shown that as we add the frames, the braces onto the frame, we are gaining, there's sort of a trade-off that results from them. The base shears, the forces that appear at the bottom of the frame go up, and this is what we're trying to optimize. Too few BRBs results in the drift, the building drifting too much. Just too many overloads the costs and overloads the foundation. And as a result, our goal is to minimize the number of BRBs while satisfying the standards, the Turkish standards. So for this, we consider a hazard level of DD2, which has a return period of 475 years, as shown on the table here. And the performance target is controlled damage. In this case, we aim for the structure to, of course, to damage, but not to the point where the occupants are disadvantaged in any way possible. So in the next case, I introduced the optimization constraints. So for each constraint, even one failure to adhere to either one of them results in the design being rejected. Number one being the base shear, the forces that go to the bottom, as I mentioned. Number two being the drifts between each flow. And the last one is a condition that is stated in the earthquake codes of the country, the plastic hinge rotation. So the structure on this page, we're basically giving the details of the model that were considered. A simple 2D model, of course, made of a reinforced concrete model. The story height being 3 meters, the bay width 5, and the columns each being nonlinear fiber sections to depict the nonlinear characteristics of reinforced concrete. And of course, the analysis type is the nonlinear static push-up. Here, we also break down the genetic algorithm used and the stages involved, the number of BRB placements configurations, that is. Afterwards, we simulate the nonlinear push-up for each configuration, check the constraints, and afterwards, we look for convergence to find the minimum BRB count, which stabilizes over generations. Thereafter, we move on to the selection and crossover, breed the designs, mutate over new solutions, and then count the BRBs used, with the lower one being our optimal solution. So here we basically cover the combinations over the configurations, 0 being no braces, 1 being one being a brace being installed. So out of all these 16 combinations, only 2 end up passing, and that's obviously, you can tell that if we put too many, it fails due to the base shears being too high. If we don't put any of them, it fails as well due to the drifts being high and the hinge formation. So where are we right now? What I showed you previously were just the preliminary results. The analysis and the refining of the code is still underway. And despite this, everything is still going as predicted. And finally, what do we expect? What do we hope to gain out of all of this? The test frame, as I said, is a two-story frame of 2 bays, and the BRB is considered a 4, combinations being 16. So the target here would be for us to extend it to higher, multi-story frames or high-rise structures. We include the BRBs, and therefore the combinations increase as you expect, but we need it to be automated, because doing it iteratively is really time consuming, and no one has the time to go through that. Time is very valuable in this case. As a result, we use the genetic algorithm to one-shot the response, the answer.
Okay, very good.
And for the conclusions, we have adding the BRBs without optimization risk overloading the foundation, as was previously shown. A constrained single objective genetic algorithm finds the minimum cost code-compliant BRB layout, and the Turkish Building Earthquake Code hazard level of DD2 provides 3 clear enforceable design constraints. And here we have the OpenSeals Pi nonlinear pushover analysis evaluation engine for each candidate design for this study, of course. And the 2-story concept will validate the logic before scaling to multi-story frames. Thank you, and I really appreciate your time.
Thank you very much for your presentation, Mr. Clifford. We can move to the next presentation. But I have a fast question, 1 minute, about the objective function of your design. I see there is also a cost, I think in the last slide. So
I can get back to it if you wish.
Yeah, of course, that's gonna be better. All right, we can move to the next presenter, Mr. Faizullahman Ishaq. If he's here, he's going to talk about the defect and trapping center in PCCVD, diamonds, energy levels, and charge transport impact. Yes, please, you can continue or proceed.
Can you hear me?
Yes, we can.
Okay, thank you very much. So I would like to, and can you see the presentation, yes?
Yeah, we can. Thank you.
Okay, so I would like to talk about shortly about the defects and trapping centers in PCCVD diamond. Sorry, I'm using 2 screens, so I will look to the presentation on the other screen if it doesn't come directly.
It's fine. It's fine. Just proceed.
Okay, so it's about the defects and trapping centers in polycrystalline diamond. And the effect of these energy levels on the charge carrier transport. Okay, so I'm Faiz Ishaq, basically the PhD student currently in Dukuz Ilul, but I'm stationed in Germany in TU Dortmund University for last 4 years. I will come to the applications of diamond, that why it's very important. So it's radiation hard, it's temperature resistant, and it's chemically inert. It has the large band gap, and it has high charge carrier mobilities and saturation velocities. So all these properties make it a good sensor material for the radiation sensing in the very high rate where the particles or the radiation flow intensity is very high, and it's at very high temperatures, for example, in the fusion or other kind of reactors, and high radiation environments, because it's radiation hard, because it's chemically inert, because it's resistant to higher temperatures. So it's a very nice sensor candidate material. And the application fields are, for example, high energy physics, nuclear engineering, fusion energy, and space application, because in space we have a lot of high radiation levels, and for dark matter detection. So, sorry, I hear some kind of voice. If there is mic of someone is open, please turn it off. So near tissue equivalence in terms of atomic number and energy absorption, it's also important in medical application, because its atomic number is equal to what the atomic number in our body is, because our body is mostly made of carbon. In that sense, it's a very good candidate in radiation therapies, and also it's an emerging semiconductor substrate, because it's environment friendly. It's already carbon that is present in the nature, and the bio nature is evolved on carbon. So there is not much problem with producing a lot of semiconductors in future with carbon materials instead of gallium nitride or others, which are very hazardous and poisonous. Here you can see the WIP. I will not go to the details, but you can see that it outperforms all other semiconductor materials in many properties, in thermal conductivity. If you go to the band gap, if you go to the electron mobility, it's better. Only one is outperforming it, and in terms of hole mobility and other things. Critical electric field, it's important because if the critical electric field is you can work on higher electric fields, then it doesn't go to the breakdown. Like, okay, then in the particle detectors, we use it in the particle high energy physics because of the some properties that it has. And you can see here its pros and cons. Its pros are very much its advantages compared to the established technology that currently used in high energy physics in silicon. It's better than silicon in many aspects. The only one aspect that it's not better than silicon is it's expensive. But with time, the technology will make it possible to lower the cost of synthetic diamonds more and more. Okay, then this is an application in high energy physics. You can see these small diamond detectors here, but this is a very large detector you see. It's of course very big detector, but you can see the beam condition monitors. It monitor the condition of the beam of protons coming into the detector that will collide and produce other particles. So that it monitors the beam, its intensity is okay or not. And also the luminosity condition monitor, it's for the luminosity and the beam purposes in many big facilities around the world, like in the CERN, Large Hadron Collider, in the Atlas, in the Fermi lab, for example, or other labs around the world. Okay, I will come directly to the PCCVD diamond. In PCCVD diamond, you can see the grain boundaries, which is a big problem because it traps the electrons or holes which are drifting across the diamond. It traps there and we lose the signal. It's very important for us to characterize the effect of these grain boundaries in the detectors. And it's one of the main problems that I'm working, and our group is working with this. Okay, I think we don't need to go into detail to this. It's a small definitions. You can read it by yourself if you're interested. But I will come to the trapping energy levels. It's a diagram. You can see where there are many kind of traps present in diamonds because of the impurities like borons or hydrogen or nitrogen or something, creating many energy levels. The main interest that we have is this one, the grain boundary effect. It produces a continuous range of traps around the detector performance. It affects the detector performance, and we have to characterize it individually. So we did it, for example, we are doing it with CCD, charge collection distance measurements. And because of the time constant, I will not go to the detail, but here you can see the effect of, this is the charge collection distance or charge collection efficiency. It means like how much signal we are losing because of these boundaries. So we have a 500 micrometer thick diamond, but the charge collection distance is only 260 or up to 280 micrometer. It means that we lose almost half of the electrons during the signal drift. Not much of the electrons or holes are reaching to the electrode to be detected like the full drift. So this is the effect of these grain boundaries that we assist here for electrons and holes, both for pumped and unpumped state. Pumping is to fill these traps, but not all traps, only part of them. By irradiating it with a beta source, we call it pumping. Okay, then we do TCT experiments. I did the TCT experiment to see the drift directly. Here we can see that the whole that the electrons are unable to drift the whole thickness. If it drift the whole thickness, it would be a rectangular type thing. We will observe like this. We see in the whole this cusp, like is cusp mean like the bunch or cloud of electron or hole is reaching, or some of them, but it's not reaching at all in electrons here. But for hole, it's a little bit better, which is complemented by supported by our this data also. Here for holes, it's okay, but for the electron drift, it's not much better. And then I did some simulation because I'm implementing it in the Alpic Squared program. I'm the main contributor for this there. So we developed the code and the models that, okay, I'm sorry, I didn't mention that we developed the papers. So this paper in the archive and the data is available here for CCD. You can visit this. And also, for example, for the TCT, you can go for the details there that how it, because we need a tremendous amount of work on this to do it. And here is the data. These two are not still accessible because I need to a little bit to improve this, but it's also in the TU Dortmund research repository. You can visit maybe after a week or so. So the summary of my talk is that PCCVD diamond contains grain boundary, sp2, hybridization is there, and impurity-related defects that introduce a broad range of trapping. Therefore, each detector-grade PCCVD diamond sample must be characterized individually because it's a broad range and we don't know for which sample, which part of the range is present there. So we need to characterize it individually. And CCD measurement provides the practical detector level parameter for these effective trapping and charge collection performance. So we do CCD, we don't need to go to the electron microscope and this and that and Raman spectroscopy and this and that. And TCT measurements give carrier sensitive information. You saw like how the electron holes are drifting. And our sample pumping improves. We pumped and this pumping improved a little bit because it filled the charge carrier, the polycrystalline boundaries, the grain boundaries, the deep levels, it was partially filled there. So it enhanced the drift or the transport of the materials. So the CCD-based approach, it's reproduce the diamond pitch features of PCCVD charge collection. It's only for this purpose, but it doesn't go to the details like where are these, how is the distribution and this of these traps. For this microscopic trap identification, then if someone is interested, then we are not interested at this moment because for detector level, CCD and TCD is enough for us. Okay, for much details of this, you can visit the paper that we published in Diamond and Related Material, where I developed a model for the charge carrier drift, especially for electron. You can visit it. It's if someone is interested in Diamond and these materials. And this one is in the archive. The data is available here. Also, you can use it. You can use it for your own research. Only citing it that you took it from here. So thank you very much for your attention and providing me the opportunity to share my work.
Thank you very much, Mr. Faizullahman.
No,
Good
welcome.
presentation, good topic, diamond, expensive material. I just wonder, where did you find those samples of diamond? And it should be a big project that can provide you with diamond samples and go with your research.
Exactly. Thank you very much for your encouraging comments. The diamond we are using are the CVD diamonds. They are synthetic diamonds prepared by the chemical vapor deposition technique. That's the CVD. Yeah. And there are a lot of companies preparing it, but one founding company is in UK, which preparing its name is Element 6. Element 6, like carbon is atomic number is 6, so they put the Element 6. Name for the company, yeah. We are getting it from there, but then there is the deposition of electrodes and other things by other companies. Civic company, it's in Germany. And the founding work with natural diamonds in 1970s and before, it was done by Russians and Americans because they need this technology for their sophisticated conflicts technology
Yes,
that they use in conflict.
we can get
But yeah, now it's shifting to the semiconductor technology, to the electronic
Interesting.
material. Yeah, and for
Interesting.
this we use the synthetic diamond, not the natural diamond, but
Thank
it's still
you.
expensive. I mean,
Yeah, of course. Thank you very much. I will come later for other questions, but for now we have to move. But actually, I have to ask you all. We have one of our presenters who failed to present earlier because of some internet problem. In this section, I would ask you if you can hold on a couple, like 10 minutes. He's gonna do it fast if it's not a problem for you all, so that we
no,
can take him.
no,
If
it's
someone
not.
has a problem, he can just say it or
It's
not.
okay.
Okay, thank you very much. Thank you very much. So, Dr. Sule, you can share your presentation, then we proceed. Dr. Mohamed Sule, are you there?
Can you hear me?
Yes, we can, please.
Okay, thanks. Please. Can you see my screen?
Yes, we can, no problem. You can proceed.
Okay. Please, I would like to adjust. Okay. Okay, hi everyone. My name is Serpil. So my topic is influence of circulation of mineralized fluid in Eva South Alif. Moving forward to the presentation because of the time. So my presentation outline, as you see, we start with the introduction, the literature review about the effect of tectonics, and we talk about the literature review and study area, objectives, methodology, result and discussion, and we conclude and then some recommendation. So as we see for Niger, Niger is a reference about uranium. When we talk about uranium, always we hear about Niger. So from 1959 and 1967, Niger were experiencing with huge, extensive uranium exploration. So as you see, we in Niger, we start the extraction of uranium in around 1969, which is coming up. So now is closed. So the only is Somalia, which is performing now. So all these deposits not in the sector are located in Alif. So from the northern Niger. The difference in biologic fracture zones and the creation of patients. So we took out the transfer of mineralization is controlled by biology and surrounding formation, and the accident, especially one identified by some the previous study. So for the mechanism is we talk about the origin of uranium mineralization concentrate, especially in Eva's southern sectors, which is poorly understood. So in our research, we explore the origin of mineralization fluid as well as the structural ones that contribute to the transfer of mineralization mineralizing fluids in southern Eba sectors. So moving to the study area, so what you see from the map is Alif, and so for me, here we proceed a sampling. So we took 516 samples, which we modeled, we to determine the effect of the tectonic mineral fluid of uranium. Of uranium, and then evaluation of the code for the parameter for processing the survey data. So from the methodology, so from the it's coming. So we took the sample of organic matter, sulfide carbonate, and oxyhydroxide acid, and index varied from 0 and 0. So we calculation. So the formula is IKS is S1, and IP is index of Gazman, and P is power of the pass. We use also the ArcGIS for the modeling. So for the results, you see from the figure on the right, the presence of organic, which is significant from the south. From the south, which this funding are similar for the previous study for the organic matter parameter. Strongly considered in the western, but from the east we have the weaker concentration of the parent. For the carbonate parameter evaluation, you see is from the map, you see the distribution of the value from the western parts. You have everywhere the presence of carbonates. So from the presence is almost in the entire study area. The reformation during the diagenesis and the other the circulation of fluid transportation, uranium oxide. For the oxidation reduction, a combination of parameters. Well, that's say organic matters and oxyhydroxide to better understand the redox aspect of the study area. You see, the interface between the two parts correspond to the redox front that separate the reducing formation in the west, the oxidized ones in the east.
So, Doctor, we can work on concluding as soon as possible.
Yes, sir.
Could we go to the conclusion as soon as possible, please?
Okay. Just so one slide. So oxide is are good indicators of oxidation of medium, which is similar for the previous study. So moving to the conclusion. So the analysis of the various redox maps revealed that the mineralization of Eba salt is related with organic materials as sulfide and carbonates. But are found in the, for parent minerals is found in reduced area. Most of the EBA South mineralization was established by the redox mechanism complete with the circulation of fluid meteoric with predominant structural control. So nevertheless, we can underline a control of the scale of the region led by the Alif regional fault. The parameter fracture and the porosity of the formation's sandstone undoubtedly contributed to the transmission of mineralizing fluid in the EBA South sector. So that is our reference which we use in our study. Thank you for your attention. If there is any question, I'm glad to hear.
Thank you very much. Thank you very much. Is there anybody with a question or someone want to ask a question to our presenter? Otherwise, I would ask all of you please to open the screen to take a picture for the Congress book. Would you please switch on your cameras, please, so that we can take the final picture? Oh, 1 second. I have not opened mine. All right. Okay. I still have Mr. Clifford, Anyway. Okay, Mr. Garba. Thank you very much. It was an interesting meeting, interesting and full of information. I wish we had more than this as time so that we can talk and discuss other questions we have. We did not ask because of time constraint, but I think we can always find the opportunity to talk later in private. And by the name of science, I congratulate you all and I wish you all success, and I see you to our next session. Goodbye. Have a nice day.
Thanks so much.
You're welcome.
Thank you.